Okay, thank you so much for the intro and thank you for the introduction. It's a treat to be here. And today we'll discuss machine learning with quantum computing. And the idea for this talk is to be a very high-level overview of the field and a blueprint if anyone is interested in entering the field. Please feel free to interrupt and ask questions at any time. Let's start with the basics. And let's say that we have a task, and our task is to design a machine that can recognize objects, for example, cats. And the first thing we can do is use our human-made representation of a cat. For example, a cat is a furry animal with big eyes and a tail, and it looks very cute. And we can try to encode this representation of a cat into our machine. So this would basically be a giant if statement. So if input, return cat. This is basically machine vision circa 1980, but there are many problems with this approach, right? Chief among them, it's not very scalable because we need to build and encode human-made representations of every object everywhere, ever. And even worse, if my cat happens to have some genetic mutation and it doesn't have a tail, well, my machine will not be able to recognize the cat, even though it is still a cat. So another thing we can try is let the machine itself figure out its own representation of cats. And this representation may not be understandable or interpretable to us humans, but it will allow the machine to return cat if the input contains it. And nowadays, this is done using so-called deep neural networks. And these are models that are basically mathematical abstractions of how the human brain works. But to be very clear, this is not really how the brain works. These are just models. And they're basically layered architectures comprised of neurons connected with weights, so weighted connections. And these weights are basically like knobs that we can tune in such a way that will allow the machine to build a useful representation of cats or any object. And this is done by feeding a massive data set. So a data set of cats and dogs and planes and trains and birds. And using the output of the model, we define some cost function that quantifies the performance of the machine. And then this cost function is minimized using backpropagation. And this is a gradient-based training technique. And if we do this well, our be able to recognize cats and dogs and birds and everything. And this representation power is basically what led to the successes of machine learning in the last 10 years. So everything from machines that can play Go on a superhuman level to machines that can fold proteins. I believe AlphaFold has folded millions of proteins by now, or large language models that can interact with humans in a very engaging way. Of course, a key ingredient here is the hardware. Deep neural networks are usually ran on GPUs, and GPUs are processing units that have been originally designed for gaming. And they happen to be very good at matrix multiplication. And on the other hand, neural networks, and more importantly, backpropagation, the training procedure, can be very efficiently represented. So the convergence of these two factors is kind of serendipitous in a sense, though one could argue that the availability of data and appropriate hardware and appropriate models, all of these are just consequences of chips getting smaller in the last 50 years. But anyway, GPUs are Turing machines, right? They operate based on the laws of classical physics. They process zeros or ones. So the question is, how will machine learning look like if instead we have a machine that operates based on the laws of quantum mechanics? So it processes superpositions of zeros and ones. And of course, this means that we have access to a quantum computer. And nowadays we do have access to noisy intermediate scale, so quantum computers with 50-ish qubits, and we can access them online. And these machines are basically comprised of n qubits. Qubits are physical systems that can maintain superpositions of states. And we want to manipulate these qubits, and we do this using unitary gates. And this must be unitaries just to be able to transform the quantum state into a state, valid quantum state. In the end, we can measure the qubits. And we do this usually by defining some observable, and we want to find the expectation of some observable. And the key point here is that some unitary gates are actually parametric. So their operation depends on some parameter, for example, a rotation angle, a continuous variable that can be optimized. So in the context of machine learning, what we do is we take an image of a cat, for example. We encode this image into a quantum state using a unitary gate. Then we manipulate the qubits in some way using parametric gates. And in the end, we measure the qubits. Using some expectation of an observable, for example, we define a cost function. And again, we want to minimize the cost function. We want to obtain the best prediction possible. And this is basically what quantum machine learning nowadays represents. Though, to be fair, just like there are many algorithms, right? We have deep neural networks, we have kernels, we have nearest neighbors. There are many quantum types of machine learning models, but this is the quantum equivalent of deep learning. So this is basically a variational quantum circuit that's dependent on a parameter, and we want to optimize parameter based on data. To do this, we need 4 elements. We need data, of course. We need to define the model architecture, which basically means we need to design the unitary. How do we place these gates, these qubit gates? We need to find the training procedure, and finally, we need to test and validate our results. So the type of data that we use will be dependent on the task that we are trying to solve, right? But it falls in 2 categories largely. So it can either be classical data, so pictures of cats and dogs, planes, trains, or it can be quantum data. The difference here, of course, is that classical data needs to be encoded into a quantum state. So this is done using those unitaries, whilst quantum data is usually data that comes from, for example, a quantum sensor that was sent into the world, or it can be data from a quantum simulation. So these are quantum states. We use them directly. And once we have the data, we need to build our model. The first thing we can do is use just single qubit gates. So this means that we just place single qubit gates on each qubit, and we try to rotate each qubit separately. And this gives rise to the mean field model or the separable model. And for some simple tasks, this kind of circuits may be sufficient. But I would argue that this is actually the most important model in quantum, because let's say we've designed some fancy architecture with 1 million qubits and 1,000 gates, and then we tested against a mean field model, this simple circuit, and this simple circuit performs better. No reason to use a fancy model, fancy architecture, and I would argue that there is no reason to use a quantum computer in the first place, because these types of models are relatively easy to simulate on classical devices. So this is a very important benchmark here. Another thing we can do is, in addition to these single qubit gates, we can place entangling 2 qubit gates like C0s or CXs. And this gives rise to the hardware efficient model because C0 gates and CX gates are relatively easy to implement on both gate-based or pulse-based quantum machines. And we use this type of circuit, a hardware efficient model, to train Bayesian binary neural networks. So in this case, the neural network, the learning model, is run on a GPU. So this is a classical learning model, except it's a Bayesian model, which means that the weights are sampled from a probability distribution. And usually this probability distribution is something like a mean field Bernoulli. And this is where machine learning kind of struggles, because Bernoulli distributions are quite simple, and sometimes they're not capable to fit the dataset. So instead, what we did is replace the Bernoulli with this quantum circuit. This is also a variational distribution, right? And the weights of the neural network are actually measurements of the qubits. So they are sampled by measuring the qubits themselves. And as it turns out, this performs much better than just using a Bernoulli here. To train these circuits, if we have few parameters, by few I mean like 3, then we can use gradient-free optimization techniques like Nelder-Mead or something. But these types of surge-based algorithms do not scale very well with the number of parameters. So unfortunately, the only way to go are gradient-based techniques. The problem here is there is no quantum equivalent of backpropagation. By this, I mean there is no quantum training gradient-based algorithm that has the efficiency of backpropagation. There is, however, the parameter shift rule, and this will probably remind you of finite difference differentiation, but it allows us to compute gradients. And to do this, for each parameter in the circuit, in the model, for each phi, we need to run the model by shifting the parameter both left and right. So first we shift the parameter by some fixed value to the left, like here. We get the cost function. Then we shift the parameter to the right. We get the cost function again. And the gradient is the difference between these two. And the problem here is that this is not efficient either, because we need, for a single parameter, we need to run the model twice. And if this cost function is defined using an expectation of an observable, each of these is obtained by 1,000 runs of the circuit. So for each gradient, we run the circuit 2,000 times. And that's not super efficient. Worst of all is that even if we use parameter shift rules, despite of the inefficiency, and if we use some architecture like the hardware efficient ansatz, well, it turns out that these types of models are very expressive. And models can fit many functions. Generally, this is a good thing. Except in quantum, there is a clear link between the expressivity of the model and the disappearance of the gradients. So the more expressive a model is, the faster we are going to hit some barren plateau. And once we do this, the gradients become 0. And if the gradients become 0, then the cost function is not going anywhere. And this is quite a big problem. There are some ways to deal with it. One of them is to try to restrict of the model. And this is one of my favorite topics, but I promise no group theory here, no Lie algebra, nothing like that. But anyway, restricting the expressivity of the model means that we are using some restricted model class. This is done by encoding symmetries. And the term symmetry comes from the ancient Greek, symmetria. It literally translates to same measure. So Plato, for example, thought that the Platonic solids, the basic building blocks of the universe. They didn't know about atoms and molecules back then, of course. But ever since then, as Weil might say, symmetry has been an idea using which humans throughout time have tried to create order and beauty and perfection. And as a result, we find that everywhere, in art and architecture, in science. So for example, if you go to the Tate Modern in London, you can see exhibitions on symmetry. Symmetric buildings are everywhere. There are even theorems in psychology about why humans like symmetric objects. It's something to do with uncertainty reduction. Brains do not like surprises, apparently. And in science, well, as Anderson might say, physics is basically the study of symmetry, right? To major discoveries, everything from Noether's theorem to conservation laws and countless others. Now, in machine learning, symmetries essentially represent an inductive bias. So prior knowledge that we try to encode into the choice of an architecture, and if we do this well, we aim to improve generalization or improve procedure, or on the quantum side, try to avoid some barren plateau. In classical ML, the study of symmetries in machine learning has led to geometric deep learning, right? And many of the most powerful architectures nowadays are symmetry preserving models. So convolutional neural networks, graph neural networks, transformers that basically underline ChatGPT, any diffusion models, LSTMs, all of these are symmetry preserving models. And on the quantum side, we also have quantum convolutional and quantum graph neural networks. But how do we actually choose a symmetry and how do we encode it into an architecture? Well, let's say that we have two types of data available. We have images and we have molecules. And this is the famous, rather infamous image generated by a diffusion model that won photography competitions. And of course, humans were not very happy about that, understandably. But anyway, how do we choose an appropriate architecture to process images? Well, the first thing is that an image is Euclidean data. So this data lives on a grid. And on a grid, the appropriate symmetry is translation or shift. Because like here, I can shift this photo and it's still the same image. Or I can flip it upside down. It is still an image of two women. I can do some other transformation. It's still going to be an image of two women. And we want a model that is going to be able to reflect or rather preserve these transformations. And as it happens, a convolutional neural network does exist. So this is done using convolutional filters and pooling operations on top. And as a result, convolutional neural networks are translation invariant. Or rather, the convolutional operations are translation equivariant, but convolution plus pooling is translation invariant. And on the quantum side, we also have quantum convolutional neural networks. Just to be clear, these are not similar to classical neural networks, and they're definitely not similar to human brains. These are just quantum circuits, so variational quantum circuits that are dependent on variational parameters, but we just call them neural networks, so quantum neural networks. But anyway, a quantum convolutional model is comprised also of a convolutional and a pooling operation. So the convolution is basically placing a 2-qubit unitary in a cyclical way. And then after the convolution, we put a pooling operation by essentially reducing the degrees of freedom. So we measure parts of the qubits, some qubits remain unmeasured, until we are left with only one qubit. And we use this one qubit to make a prediction. So we repeat this until we are left with one. And as a result, this model is also translation invariant. Now, if we have molecules, well, molecules are very well represented as graphs. And on a graph, order has no meaning. It doesn't matter if this blue one is 11 or 2. This is a molecule, right? It doesn't matter how I order. Properties of the molecule do not change. The energy levels of the molecule do not change. If this is a communication network, well, the achievable sum rates do not change if I permute the devices. So order doesn't matter on a graph. And we need an architecture that's going to preserve this. And as it happens, graph neural networks do exactly this. So using message passing, which means that each of these nodes aggregates nodes from its neighbors. And then this is passed through a neural network. On top of that, we add some pooling operation. And as a result of this pooling operation, graph neural variant to permutation. Also, transformers that can be seen as fully connected graph neural networks in a sense are also invariant to permutation. On the quantum side, we also have permutation invariant or equivariant graph neural networks. So the key point here is that we place 2-qubit gates using the structure of the graph. So if this is 1, 2, 3, 4, again, order doesn't mean anything here. I'm just abusing that a bit now. So because there is an edge between 1 and 2, we're going to place a 2-qubit gate between qubits 1 and 2, then between 2 and 3, then 3 and 4. And as a result, this model will be permutation equivariant. Or we can just assume that our graph is fully connected here and just place 2-qubit gates between all pairs of qubits. and this gives rise to the so-called SN equivariant model. And all of these were examples of spatial symmetries, but many types of data in nature are actually temporal, right? They have a temporal component, everything from vital signs to quantum simulation, traffic. These are basically time series. So how can we use the ideas of symmetries if we have data that has some temporal component? The first thing to note is that time series come by sampling a continuous signal. So nothing in nature is discrete, right? Signals in nature are largely continuous, and we sample these signals in order to obtain a time series. The thing is, the rate of sampling is not always something that can be controlled. It's not something that can be fixed. So it turns out that if we have the same signal and we sample it with different rates, and we give this 2 time series to the same type of model, this model will not perform the same, even though it's the same signal, we just sampled it differently. And we do not want this. We want an architecture that is resilient to changes in sampling rates. And the model that is resilient to these changes is called a time warping invariant model. Formally, time warping is defined as some monotonically increasing and a differentiable function of time. For example, we can have linear warping in the simplest case, whereby time is multiplied by some constant. So if this constant is smaller than 1, then time basically stretches. If it is larger, it shrinks. So if this blue one is the original signal, then the red one is its time warped counterpart. Though time warping admits many more complex transformations of time, so nonlinear warping, variably changing sampling rates, jitter, clock drifts, which are very important in engineering and so on. And formally, we say that a model class is invariant to time warping if for an input x of t, it produces an output z of t, and if for an input x of c of t, it produces an output z of c of t. So it produces an equivalently warped output as the input. And this is for any time warping function. So we have our time series. We have x1, x2, xt, and we want to process this using some time warping invariant model. First, let's start with quantum recurrent neural networks. These are not invariant to time warping, but we have a quantum recurrent model, which means that we have access to 2 registers of qubits. So we have qubits B. And at each time step, xt, we are going to encode xt into the qubits in register B. Then the qubits in the B register are going to interact with the qubits in the A register. And in the end, we measure the qubits in register B. Using this measurement, we define some cost function, and we want to minimize this. The key here is that the qubits in register A are not measured. And as a result, they represent the memory of the system. So we only measure qubits in register B. And if you would like to see derivations and the math and theorems and proofs, everything is in this paper here. But if you do the derivations, it turns out that a time warping invariant recurrent model is going to apply this unitary at time t with some probability alpha. So with some probability alpha, we apply the unitary. And with probability 1 minus alpha, the unitary is not applied. So the state of the memory is not changed. And this alpha happens to be the derivative of the time warping function. Of course, the time warping function is not generally known, and the derivative is not known by extension either. So what we did is use a recurrent neural network. This is a classical model, again, that's going to learn this probability. So the role of the classical recurrent model is to serve as a learnable gating mechanism. And as a result, this time warping invariant model is able to learn to retain or forget information in a data-driven manner. So the model learns what information it needs in order to predict the sequence for the next prediction. And there are also stochastic counterparts of quantum recurrent models. And this means that instead of using an expectation of an observable, for which we need to run the model 1,000 times, we just use a single outcome of measurement. So this is found using a single run of the circuit. Again, the difference is the training procedure, but the time warping invariant model also has a learnable gating mechanism that can allow the recurrent neural network to learn what information it needs. Okay, to see an example, let's say we have this cosine wave, and we warp this signal with linear warping. So time is multiplied by a constant, and that means that each element in this cosine will be repeated 1/8 times. And that's why we have these step functions here. And we want to train a model to remember the cosine wave, or rather the time warped cosine waves. And if we do this and we use a quantum recurrent model that is not invariant to time warping, well, it doesn't do so well. If we use a classical LSTM, it doesn't do so well either. But if we use a quantum model that is invariant to time warping, then the loss function is much smaller. And this is for both values of the time warping coefficient. And the interesting thing here is that the case when we don't know the warping in advance, so we have to use a learnable gating mechanism, performs much better than the case when we know the warping in advance. And this kind of persists throughout all of the experiments. And this is the same for the stochastic counterpart. So again, here we just make predictions with a single run of the circuit, not 1,000. But the time warping invariant model performs better than the standard recurrent neural network. And for another experiment, we tried to predict quantum dynamics. So here we have a 3-qubit open quantum system. Its evolution is governed by the Lindblad master equation. And we want to predict the future evolution of the system. And we also warp time. So instead of t, we use square root of t. So that is this figure on the right. That's why time looks different here. And we want to train a model that's going to predict this signal. Again, if this model is a quantum recurrent neural network that's not invariant to time warping, then the loss function will be quite large. And LSTM does a bit better. But the recurrent model that's invariant to time warping does the best. And again, the model that has a learnable gating mechanism does better than the case when we know the warping in advance. So we know this probability alpha in advance. And that's not something that I expected at first. And these results show exactly that. So the learnable gating mechanism kind of approximates the probability alpha. It's not exactly the same, but we suspect it's also able to compensate for some approximations made in the derivation. And that's why having a learnable gating mechanism is better than knowing the time warping in advance. So unlike the spatial symmetries before, class invariance is kind of distinct. So time warping invariance is equivalent to class invariance. And it's kind of different because it's more of a peace of mind result in the sense that I cannot give you a group, I cannot give you a domain that describes time warping invariance, but it basically says that if there is a model in this model class that can fit the original signal, then if I warp the signal, there is also a model in this class that can fit the warped signal. And that's something that we need. Again, we don't want to have the model perform differently for 2 changes in the sampling rate, for example. And the most important thing here is that this is a restricted model class. Again, we want to improve the training procedure. And by restricting the model class, we try to avoid barren plateaus. Okay, so we found our model, we have data, we trained it. So now we need to test the model. And this is very, very important. And of course, one can always be used are classical models that are equivalent to the one that we are developing, and this should be included whenever possible. And I would argue that a separable model, the first one that we saw, should always be included as one of the benchmarks. If it performs better, then maybe we don't need to have a quantum model in the first place. And one of my pet projects now is compiling a set of golden data sets that we can all use to benchmark our models, but this is not ready yet. This is just work in progress. Okay, I'll start wrapping things up now. It's very premature to think about practical use cases of quantum machine learning models. We don't know what the practical use case here is. It's very much fundamental research at this stage. I personally see it as a potentially powerful modeling technology in the AI for science domain, but it's too soon to tell, and that's because we don't know the role of scale. Right now, we have 50 qubits available. We don't know how these models are going to behave when we have 1,000,000 qubits. But still, it's very important to be very principled at this stage. So benchmark the models properly, use as many as possible, because we need to know what models are worth scaling. For example, ChatGPT is kind of based on a paper called "Attention is All You Need." And the size of the model in this paper is much smaller than ChatGPT, but they have better performance than 10 really good benchmarks. And it's always useful to look at tasks for which classical machine learning is struggling. We don't usually do this, but I think there is no need to reinvent the wheel, so maybe this can serve as food for thought for the audience. Okay, with this, I'm going to stop. And if there are any questions, please go ahead. If not, this is my email. Feel free to reach out for anything. And thank you.